Every single day, your heart moves enough blood to fill a small swimming pool. Not over your lifetime. Not over a year. Today, around 7,500 liters. And here's the strange part. Your heart never pumps at one steady speed. Walk upstairs, and it speeds up. Sleep, and it slows down. Get scared, and it jumps instantly. The flow keeps changing every second. So here's the mystery. If the speed is always changing, how can anyone know the exact total amount of blood your heart pumps in a day? That question leads to one of the biggest ideas in mathematics. The integral. Let's start simple. Your heart pumps a tiny amount of blood every beat. Tiny amount. Tiny amount. And when you add all those tiny amounts together, you get the total blood moved in a day. That's the core idea behind an integral. Many tiny changing amounts, adding together into one big total. Now, let's make that more concrete. At this moment, your heart might pump around 80 milliliters of blood per beat. And maybe it's beating about 70 times every minute. So right now, your heart is moving roughly 80 times 70 almost equals 5,600 milliliters per minute. About 5.5 liters every minute. Good. We know what's happening right now. But the problem is, right now doesn't last very long. A minute later, your heart speed has already changed again. Now here's the mistake almost everyone makes first. If your heart pumps about 5.5 liters every minute, and there are 1,440 minutes in a day, then maybe you can just multiply them together. That gives around 7,900 liters. Close. But not correct. Because we secretly pretended something false. We acted like the heart stayed at one speed for the entire day. It doesn't. Your heart is constantly changing. Faster. Slower. Faster again. So one single number can't perfectly describe the whole day. We need a better idea. Imagine watching your heart beat throughout the day. Every beat pumps a tiny amount. Some beats pump a little more. Some a little less. But each beat still adds something. So instead of pretending the heart stays constant, we simply keep adding every tiny amount together. Beat after beat. Minute after minute. Hour after hour. Tiny amount. And slowly, a giant total begins to build. That's the real idea behind integrals. Not one giant calculation. Just lots of tiny changing pieces being added together. Now picture this on paper. Draw a line that rises and falls with your heartbeat through the day. Up when it races. Down when it rests. Every tiny amount of blood is a thin strip standing under that line. Tall strip when the heart pumps hard. Short strip when it rests. Stand them side by side. All day long. Together. They paint a shape. And that shape is the total blood. Mathematicians call that shape the area under the curve. Area just means the size of that painted region. This way of seeing integrals, as area under a curve, shows up across calculus and science. And the smaller the pieces you track, the more accurate your answer becomes. Imagine trying to estimate rainfall during a storm. If you only check once the entire day, your estimate won't be very good. But if you check every hour, it's better. Every minute? Even better. Every second? Better still. The more closely you follow the changes, the closer you get to the truth. The same thing happens with your heart. the total starts getting more and more accurate. 7,900. Then 7,600. Then 7,520. Then 7,501. Each new estimate barely changes the one before it. The answer starts settling into one stable number. That settling in has a name. Mathematicians call it a limit. There's a whole video on limits. Links up top. And mathematicians realized something incredible. Even if something keeps changing continuously, you can still find the exact total. All you have to do is keep adding the tiny changes together. That entire process has a name. It's called an integral. And mathematicians write it using this symbol. A stretched out S. Drawn tall. You'd say it like this. The integral from a to b of f of x times a tiny piece of x. Now, let's pin down what each piece points to. A is where you start. For the heart. That's the start of the day. B is where you stop. The end of the day. F is a function. Just a rule that takes an input and hands you back a number. So f of x is the rule that gives you the pumping rate at any moment x. The tiny piece of x is one thin slice of time. And the stretched s means sum. Because an integral is really just a sum. A very, very careful sum. So, in plain English, an integral is a way of finding a total by adding together lots of tiny changing amounts. That's it. That's the whole idea. And once you see it, you start noticing integrals everywhere. Your phone battery drains little by little throughout the day. Rain fills a bucket drop by drop. A car travels tiny distances moment by moment. Your bank account changes transaction by transaction. Tiny changes, building into a larger total. Same idea every time. Now here's where calculus becomes beautiful. A derivative tells you how fast something is changing right now. An integral runs the other direction. It takes all those tiny changes and rebuilds the full total. One breaks change into pieces. The other puts the pieces back together. And, unbelievably, those two ideas turn out to be perfect opposites. Why? How can two ideas that seem completely different fit together so perfectly? That's the fundamental theorem of calculus. And it might be the most surprising idea in all of mathematics. Thanks for watching. See you in the next one.